Students, today we will discuss the second lecture of UV visible spectroscopy, which includes selection role for electronic transition, some terms used in UV visible spectroscopy, and factors which can affect the absorption band. Now, I am going to the main lecture. Selection rule for electronic transition. Electronic transitions may be allowed or forbidden transition, as reflected by appearance of an intense or weak band according to magnitude of epsilon max, and is governed by the some selection rules. These selections are as follows. First, spin selection rule. Delta S is equal to 0 for transition to be allowed. Spin orientation not be changed. That is, no spin inversion occurs during these transitions. Thus, S to S transition and singlet to singlet transition and triplet to triplet transitions are allowed, whereas singlet to triplet and triplet to singlet transitions are forbidden transitions. Second, Laporte selection rule, where L should be equal to plus minus 1. These are of two types. Molecules having a center of symmetry transition within a given set of p or d orbitals are forbidden. But there is a change in symmetry. That is, transition can occur only between the states of opposite symmetry. Laporte allowed transitions is G to U or U to G, where G stands for graded compounds with a center of symmetry and U stands for ungraded compound without a center of symmetry. So, for that case, the Laporte forbidden transition G to G transition and U to U transitions are Laporte forbidden transitions. Thus, S to P and P to D are allowed, but S to S and P to P are forbidden. And thirdly, H nu must be equal to delta E, transition energy. This is the basic principle of UV visible spectroscopy, that photon match energy gap between the ground and excited states. That's why electronic transitions occurs in a particular frequency. Next, important factor, fourth factor, delta mu is not equal to 0. That is, anisotropic charge displacement. According to this selection rule, the transitions are forbidden which give no change in dipole moment and therefore will have almost zero intensity. Selection also depends on the order of magnitude of the molar absorptivities, where lambda epsilon max is equal to 10 to the power 4 to 10 to the power 6 will give high intensity absorptions, and whereas this value will be 10 to the power 3 to 10 to the power 4, this will give low intensity absorptions, and for 0 to 10 to the power 3 is forbidden transitions. Some terms used in UV visible spectroscopy, these are chromophore. What is the chromophore? The part of the molecule responsible for imparting color is called as chromophore. Or functional groups that contains multiple bonds capable of absorbing radiations above 200 nanometer due to N to pi star transitions and pi to pi star transitions. For example, nitro, NO, CO, C, double bond N, C triple bond N, carbon double bond, C double bond S, etc. At the chromophore. And Auxochrome, another important term for UV visible spectroscopy, the functional groups attached to the chromophore, which modifies the ability of chromophore to absorb light, altering the wavelength of or intensity of absorptions. Or we can say the functional group with non-bonding electrons that does not absorb radiation in near UV region, but when attached to a chromophore, alters the wavelength and intensity of absorption. For example, benzene has the lambda max 255 nanometer. But if OH is attached to the benzene ring, then it will form phenol. Then the lambda max of phenol would be 270 nanometer. And if we add NH2 group to benzene ring, that will form aniline, and the lambda max of aniline will be 280 nanometer. Next, some important absorption and intensity shifts. First of all, bathochromic shift. When it is also called red shift, when absorption maxima, that is lambda max of a compound, shifts to a longer wavelength, it is known as bathochromic shift or red shift. Hypsochromic shift. When absorption maxima of a compound shifts to shorter wavelength, it is known hypsochromic shift or blue shift. And in terms of intensity, there are another two terms. One, hyperchromic effect. When absorption intensity of a compound is increased, it is known hyperchromic shift. And when absorption intensity of a compound is decreased, it is called hypochromic shift. Here is a picture where we have clearly shown the bathochromic shift, hypsochromic shift, and hyperchromic shifts. Firstly, here the lambda max value is being increased. So this is bathochromic shift or red shift. Here lambda max increases, and here the lambda max is being decreased. It is going to the left side. So this is hypsochromic shift or blue shift. Here lambda max decreases, and here epsilon max, that is intensity increases. It is hyperchromic shift, and here intensity decreases. Here it is hypochromic shift. Okay. Next, there are some factors which can affect the position of UV bands. I am discussing some factors which can affect the position of UV bands. These factors are conjugation, effect of steric hindrance, effect of geometrical isomer, S-cis Cisoid and Transoid conformations, exocyclic double bond, substituent ring residue, solvent effect, hydrogen bonding, sample pH. First of all, we are discussing about the fact conjugation. If combination of two or more chromophores make the system conjugated, the absorption maxima will be shifted to a longer wavelength or shorter frequency. Conjugation increases the energy of the HOMO and decreases the energy of LUMO. So, less energy is required for an electronic transition in a conjugated system than in a non-conjugated system. Here, energy is showing in this direction, and for the case of ethylene, consider this is the energy gap between the HOMO and LUMO. And in the case of butadiene, when two ethylene molecules are combined to form butadiene, then the energy gap between the HOMO and LUMO for the butadiene will be delta E2. Then the energy gap is higher in the case of ethylene, than the energy gap between the HOMO and LUMO in the butadiene. We are seeing that the lambda max value of ethylene is 170 nanometer, whereas butadiene, lambda max value of butadiene is 217 nanometer. So due to decrease in energy gap, we know there is a important relationship E and lambda is equal to H nu. So E is equal to H into C by lambda. So E is directly proportional to 1 by lambda. So lambda is uh, with the increase of energy, lambda will decrease, and with the decrease in energy, lambda will increase. This is the beautiful relationship between the energy gap and the lambda max. Here the picture showing carbon carbon double bond. When two carbon double bond, two ethylene moiety will attach among themselves to form butadiene, then energy gap will decrease. If we add another ethylene molecule to form the three carbon carbon double bond, then energy will gradually more decrease. So the energy gap in this case is lowest among this energy gap of these compounds. For the carbonyl compounds, when ethylene carbon carbon double bond and carbon double bond oxygen, that is carbonyl group will attach to them, and carbonyl group with conjugation with the carbon carbon double bond to form alpha beta unsaturated carbonyl compound. The pi to pi star transitions shift at a longer wavelength compared to the unconjugated ethylene moiety. Both pi to pi star and n to pi star transitions shift to a higher wavelength compared to the unconjugated carbonyl compounds, but the energy of the n to pi star transitions is not decreased as rapidly as that of the pi to pi star band. With the increase in conjugation, n to pi star bond will be shifted towards the more intense pi to pi star band system. Here, this is the picture. This picture shows the molecular orbital of alpha beta unsaturated carbonyl system along with the isolated carbon carbon double bond and carbonyl compound. Now the second factor is steric index. We know that the position of lambda max and its intensity depends on length and effectiveness of the conjugated system. For effective electronic conjugation, the molecule must be planar in conjugation. Due to distortion of planarity, owing to the presence of any auxochrome may lead to the red or blue shifts depending upon the nature of the distortion. For example, usual calculation of lambda max value does not match with its expected value. The diene, 1,3-butadiene, for example. So, here shown below, we have shown here the 1,3-butadiene, usual calculation for 1,3-butadiene, it is usual calculation 1,3-butadiene, usual calculation. And the distortion of chromophore, its absorption at 220 nanometer. This blue shift is due to distortion of planarity. It suffers from loss of conjugation. Similarly, for this case, verbenine, we are seeing that the lambda max exhibited 245 nanometer. Its expected lambda max value is 227 nanometer. So due to distortion, the lambda max value is being changed. Next, geometrical effect of geometrical isomers. In general, trans isomers absorbs at higher wavelength and epsilon max is longer than for that of the cis and mixed isomers. This is the trans steel beam, and here we are seeing that the head two exocyclic double bond had two exocyclic double bond, and this is 1,3-butadiene. The lambda max value of trans steel beam is higher than that of the cis steel beam due to steric effect because of effective pi orbital overlapping in the trans steel beam helps in to attain the coplanarity of pi system more readily than in cis steel beam. However, due to crowding, the presence of bulky groups on the same side of the double bond in the case of cis steel beam, crowding, so the planarity becomes destroyed in the case of cis steel beam. Here we are discussing about the S-cis and S-trans conformation and its effect on UV visual band, position band. This is the S-cis form, and due to rotation about C2, C3, it will be converted into S-trans. This is the heteroannular dyne, lambda max value 235 nanometer, and in the case of homoannular dyne, the lambda max value is 273 nanometer. Since pi electrons in the cis isomer are more crowded, more repulsion occurs between them. This leads to instability of the ground state energy level. But this inter-electronic repulsion is reduced when an electron is promoted to antibonding molecular orbital. Consequently, instability becomes less in excited state. Hence, lambda max is higher and epsilon max is lower in cis conjugated ins. The lower value of epsilon max is attributed due to shorter distance between the ends of the chromophore. As homoannular dyne in S-cis in, it absorbs at longer wavelength with lower intensity than heteroannular dynes having S transition. For the exocyclic double bond, due to presence of double bonds outside the ring, that is called exocyclic double bond, chromophore becomes distorted. Consequently, the ground state energy level becomes unstable. And but promotion of one electron to pi star molecular orbital makes the excited state less unstable. Hence, bathochromic shift occurs owing to intense lambda max value. This is the compound. For this exocyclic double bond, 5 nanometer lambda max value will be increased and overall value will be 232. Substituent and ring residue. When a substituent or ring residue is attached to a conjugated chromophore, absorption maxima is shifted to longer wavelength. Magnitude of shift depends upon the nature of the substituent. For example, alkyl group and amino group shifts lambda max by 5 nanometer and 50 nanometer respectively due to small inductive effect of alkyl group and strong resonance effect of amino group. Here is an example where think this separate portion, for this separate portion the value will be 217 nanometer, and this is the ring residue. This will be the another ring residue. For this two another ring residue, the value will be 5 into 2. And for this exocyclic double bond, this value will increment of value will be plus 5 nanometer. And for this ring residue, two ring residue, the value will be 2 into 5, 5 into 2 for two ring residue. And the total value will be 232 nanometer. For the similar case, we will get base value 217, and for this exocyclic double bond, 5 nanometer value will be increased, and for two substituent, the value will be 5 into 2 nanometer. For two ring residue, 232 nanometer will be the total value of lambda max. Now, I am coming to the point solvent effects. Polarity of the solvent has marked effect on lambda max and epsilon max value of alpha, beta unsaturated carbonyl compounds. But it is not so much important for conjugated dyeing and aromatic system. Why and how? Both the pi and pi star molecular orbitals get stabilized in polar solvent. This is the energy gap in the case of pi to pi star transition in non-polar solvent, delta E value, and this is the delta E value for polar solvent. The greater the polarity of the solvents, the greater will be the stabilization of the orbital. A pi star molecular orbital is more polar than pi molecular orbital. The former is more stabilized in polar solvents than latter. So electronic excitation energy, that is delta E, for pi to pi star transition should be lower in polar solvents than in polar non-polar solvents. Lower delta E means greater lambda H. Hence, in polar solvent, bathochromic shift takes place. Among the N, that is non-bonding electrons, pi and pi star molecular orbitals, non-bonding molecular orbitals gets maximum stability in polar hydroxylic solvents. So electronic excitation energy, that is delta E, for N to pi star transition is higher in polar solvents than in non-polar solvents. This is the energy. This direction shows the energy. This is pi in polar solvent, pi, N, and pi star. In the case of non-polar solvent, after stabilizing, this is pi molecular orbital and this is N molecular orbital, as N gets the maximum stability in polar hydroxylic solvent. So from the picture we are seeing that the N gets the maximum stability, and this is the pi star. So in this case, molecules with lone pair, that is non-bonding electrons, are able to interact with polar protic solvent to form hydrogen bonding, and this interaction is greater in ground state than the excited state. So the ground state is stabilized more than excited state, and hence N to pi stars will demand more energy than in non-polar solvent. So lambda max will be shifted to lower wavelength in blue shifts. That is blue shift. Now the effect of sample pH. pH indicators used in acid-base titration change its color due to change in chemical form of the indicator compound at particular pH. Here, this is a very nice example of phenolphthalein. Phenolphthalein is a weak acid, gives anion when it dissociates in alkali. More resonance stabilization of excited state leads to the bathochromic shift, and the hypsochromic shift occurs when if the ground state is more resonance stabilized. So it is colorless in its unconjugated state, but it is pink in alkaline. At acidic and neutral pH, The equilibrium shifts to the left and concentration of the anion is too low to observe the pink color. However, under basic conditions, the equilibrium shifts to right and concentration of anions increase and we observe the pink color. So, use of suitable buffer is needful during recording of UV visible spectra. The absorption spectra of certain aromatic compounds such as phenols and anilines change on changing the pH of the solution. This is very good example. This is phenol. This is on basic medium phenoxide ions due to resonance it gets stabilized and its lambda max will be 210 to 235. That is bathochromic shift. Phenols and substituted phenols are acidic and change lambda max value upon the addition of a base. If the phenolic portion is removed, we get phenoxide ion. In the phenoxide ion, lone pair on the oxygen will participate in resonance, due to which the energy difference between the HOMO and LUMO orbital will decrease. As a result, there will be shifting of bathochromic shift to longer wavelength, along with the increase in intensity of the absorption. Now, the effect of sample concentration. We know from Lambert-Beard's law, sample concentration is proportional to the intensity of the absorption. But at high concentration, due to molecular interaction position and shape of the absorption bands changes. Consideration of such effect is very much needful for quantitative work. Effect of temperature. Although the effect of temperature is not so important, however, simple thermal expansion of the solution may change band intensity. Hence, for getting more accurate results, the spectrum needs to taken at a specified or constant temperature. There are three main criteria may be summarized as the general effect of temperature on solution spectra. Number one, with decrease in temperature, band sharpness increases. With decrease in temperature, no change in position of absorption maximum or moves very little towards the longer wavelength side is observed. The total absorption intensity is approximately does not depend on the temperature. This is the temperature graph, lambda max value, effect of temperature, lambda max change of lambda max value with the temperature. It is well known fact that the vibrational and rotational states are temperature dependent. When decreasing with temperature, vibrational and rotational energy states of the molecule decreases. Occurrence of absorption of light is observed at lower temperature, due to which smaller distribution of excited states results, which produces fine absorption bands than that of at higher temperature. It has been also observed that the position of one band maxima do not shift so much with increasing temperature, but tend to shift in lesser extent towards the bathochromic shift. Some known color in our usual life. What we see in our daily life is the complementary colors, those which are not absorbed but reflected. This is originated from color wheel. Beta carotene. This is very well known compound for the chemist. Lambda max value of its is 455 nanometer. In the far blue region of the absorption region of the spectrum, this is absorbed. The remaining light has a complementary color of orange. Lycopene. Lambda max for lycopene is 474 in the near blue region of the spectrum. This is absorbed and complement is now red. This is indigo. For indigo, lambda max value is 602 nanometer. In the orange region of the spectrum, this is absorbed. The complement is now indigo. This is our very familiar colors. This is dye, azo dye, most common class of colored organic compounds. We are seeing that the dye substituted aromatic compounds here. Here the effect of opposite groups is greater than the sum of the individual effects. This is compound color, para red, first brown, and sunset yellow. This is fulvene. Fulvene is yellow in color, but benzene is colorless. Why? The ground state of benzene is stabilized compared to its excited state by resonance, whereas fulvene is stabilized in ground state. Thus, the energy requirement for electronic transition in the case of fulvene is lower than that of the benzene. Hence, fulvene absorbs at longer wavelength, due to which it is yellow in color. And owing to absorption of benzene at lower wavelength, it is colorless. Thank you very much for your patience sharing. This is some pictures of our online class with our students in this lockdown period. Please wait. Please see this picture video, the online class in this lockdown period with our students. Thank you very much.